Hello, everybody. Thank you very much for joining this seminar. My name is Gal Oren, and I'm advising this work by Professor Leonid Barenboim and Professor Michael Elkin. Today, I would like to talk about some last results we achieved in my research in distributed management algorithms for heterogeneous computing system and networks, which are our state-of-the-art algorithms for fast distributed backup placement in sparse and dense networks. My talk will be divided to 6 consecutive contents. We will start with some intro to the topic. Then we will move to the algorithms for relatively simple structures as trees and forests, and more complex ones as bipartite graphs. Then we will generalize our results to an imported graph family of graphs with bounded arboricity. And we will also show how old school, we took a complex algorithm and turned it into a very simple one while only improving performances, and also use those algorithms and improvements to some very important applications. So let's start to understand the problem and why it's so important. We will start with some terms. We consider the backup placement problem in networks in the congest distributed model, given a network graph GVE, in which each vertex represents a processor and has a unique ID, and the edges represent communication lines on which message of size of O log n can be transferred. As we said that graphs with neighborhood independence bounded by a constant are a special focus for us, it's important to understand what are those graphs. Neighborhood independence is the maximum number of independent neighbors a vertex in the graph has, while two vertices considered independent from each other if there is no edge connecting them. More intuitively, while looking at each vertex and divide its neighbors to clusters, we ask, what is the minimum amount of clusters we can divide those neighbors such that in each cluster, all of the vertices will be connected components? For example, a bounded neighborhood independence can be exemplified in the diagram when a vertex V belongs to at most 3 cliques. As this family of graphs only restricts the number of independent nodes in each neighborhood, it is therefore a generalization of the UDG, QUDG, and UBG graph models, which are essential models for real networks. More known ones are social networks, claw-free graphs, and line graphs. For example, claw-free graphs, which is a graph that does not have a claw as an induced subgraph, when claw is a star graph with 3 edges, 3 leaves, and 1 central vertex, has bounded neighborhood independence of 2. Anyway, as you can see, the model is very inclusive. So we finally reached to the backup placement problem. This problem was introduced by Halldorsson, Kohler, Patt-Shamir, and Rawitz in 2015. In terms of graph theory, the problem in its simplest form is defined for a network graph GVE as follows. Each vertex V in V is selecting a neighbor such that the maximum number of vertices in V that select the same vertex is minimized. The problem is well motivated by computer networks whose nodes may have memory faults and wish to store backup copies of their data at neighboring nodes. But neighboring nodes may incur faults or be overflowed as well. And so the number of nodes that select the same backup node should be minimized. This way, if a backup node incurs faults, the number of nodes in the network that lose data is minimized. Put theory aside, why this problem is so important for real life and actual problems. So the possibilities of an absent node, damaged communication link, or missing data are unavoidable in wireless networks for many causes, environmental and internal alike. As today's IoT networks grow in scale and there is a need for high-rate sampling, the problem gets even worse, since those requirements are mostly dependent on the hardware and the wireless settings. Moreover, a proper backup placement allows each vertex to perform a backup to a neighboring node, rather than a more distant destination, and thus improves network's performance. In addition, nodes' memories are used to the minimum extent for the purpose of backups, which makes it possible to maximize the memory available for other purposes of the vertices. Let's take a look on some basic examples. On the middle, you can see a cycle graph. The optimal backup placement solution would be if one node selects its succeeding neighbor to be its backup node, and by that, the maximal backup burden for each node would be of only 1 unit, a good result. On the left, you can see a star graph. The optimal solution will force all the nodes to choose the center node, beside the center node itself, to be its backup node. And by that, the maximal backup burden would be of the size of v-1, a less good result. On the right, you can see a rooted, unoriented tree. The optimal solution in this case forces all the nodes to choose their parents, besides the root, to be their backup nodes. By that, the maximum load is delta. So when we consider reality, we can understand the problem in a much fine-grained manner and ask the question less formally by how exactly to transfer the data outside of the loaded area dynamically to a less overloaded area. How to do so in a distributed fashion. How to guarantee this process will work in any network conditions. And most importantly, how to do so fast and best. Let's start from the end. I would like to present a short and conclusive comparison of our results to what has been previously been achieved in the field of symmetry breaking problems in different types of graph topologies, as you can see in the header of the table. We show that O1 backup placement can be computed in O1 rounds in certain wireless networks, social networks, call-free graphs, and more generally, in any graph with neighborhood independence bounded by a constant. On the other hand, we consider sparse graphs, such as trees, forests, planar graphs, and graphs of constant arboricity, which we will later define, and obtain a constant approximation to backup placement in O log n rounds. Moreover, our algorithms are based on relatively simple internal computations, which make them especially appropriate for implementation in networks with limited resources, such as sensor networks and Internet of Things. The best previous results are those for general graphs, due to Halldorsson et al. These are randomized algorithms with polylogarithmic running times and approximation ratio of O log n divided by log n. In the current network, however, all our algorithms are deterministic. We start our solution to this problem regarding oriented trees, extend it to forest, and then extend it to very dense graphs. The tree backup placement is as simple as possible. The procedure receives a tree TVE as input. Each vertex that is not a leaf selects an arbitrary child for the backup placement. Each leaf selects its parent for the backup placement. All these selections are performed in parallel within a single round. No complications. We can clearly see that as forest consists of a disjoint union of trees, the above algorithm can be directly extended to a forest of trees in which vertices know their parents by executing the algorithm in parallel on all trees. But we can extend this technique to graphs that are very dense, as opposed to trees and forests. To this end, we construct a forest cover of the input graph in O1, meaning we achieve a subset of edges without cycles, such that each vertex is the input graph belongs to at least one edge in the subset. We do so by computing a forest cover of any input graph G, such that trees of the forest are vertex disjoint. This can be done by extending the algorithm of 𝓒𝓞𝓝𝓖𝓔𝓢𝓣 and 𝓒𝓞𝓝 for delta forest decomposition. For simplicity, we describe our algorithm for a tree T in the forest. Obviously, if there are more trees, the algorithm should be executed on all trees of the forest in parallel, while each vertex is aware only of the execution in the tree T it belongs to. So it goes like that. Each non-leaf vertex in T selects one of its children arbitrarily. Then each leaf V in T selects a siblings W of V in T with the property that there is an edge connecting them and that the ID of V is bigger than the ID of W, and also that there is no other sibling Z of V such that there is an edge connecting them, and that the ID of Z is smaller than the one of V and bigger than the one of W. If there is no just sibling W, then V selects its parent. Now we will show how for graphs with bounded neighborhood independence, the algorithm provides a good backup placement. So since each vertex can be selected only by its children, by its siblings that are connected to it in G, and by its parent, and also cannot be selected by vertices outside T, we obtained that for any graph with neighborhood independence at most C greater than 0, and T a tree in a forest cover of G, then each vertex of T is selected by at most 2C plus 1 of its neighbors in G. This is demonstrated in the diagram on the left. Note that addition of vertices both in the siblings and the children level will result with an inevitable edge to some other sibling of children, and thus they will not choose our vertex. This represents a very good load per each vertex, as it is constant. Moreover, the distributed fashion of the algorithm ensures running time of O1 and message size of O log n. Now, after dealing with dense graphs, we move on to devise a backup placement algorithm for bipartite graphs. Bipartite graphs are motivated by client-server systems, in which each client may connect to a bounded number of servers, but each server has an unrestricted number of clients. In the right diagram, U is the set of clients and V is the set of servers. As you can see, the clients group can connect to several servers, while servers must allow connection from many clients. This is a good reflection of a real scenario of usage in the client-server model, and we use it in our basic assumptions in our solution. So as you can see, the P2P network is more related to dense graphs, which previously we showed a solution to. Now we are moving forward towards more sparse graphs, such as the client-server model, and tries to find a solution to this case using an analogy to the bipartite graphs. For now, we assume that all vertices know the load value T of the optimum backup placement, meaning the maximum number of selected vertices in an optimum solution. The maximum degree of vertices in U is bounded by a parameter A, and the maximum degree of vertices in V is unbounded. Vertices also know A and N. The goal of our algorithm is obtaining a maximum load of OAT. To this end, each vertex of V may select for a backup an arbitrary neighbor in U. Since each vertex in U has at most A neighbors, the maximum load on vertices of U is going to be at most A as well. It remains to define an algorithm for the vertices of U. The algorithm goes like that. It proceeds in phases and exemplified in the diagram while 2AT equals 4. In each phase, each vertex in U that has a neighbor in V with degree at most 2AT selects such a vertex. The selection is arbitrary if more than one such a neighbor exists. Next, we remove from V all vertices of degree at most 2AT and also remove from U all neighbors of vertices that have been removed from V. Note that all these vertices of U have already made selections in V, and note also that once some vertices are removed, certain vertex degrees become smaller. Next, we proceed to the next phase that is performed in the same way. Specifically, vertices in U with neighbors of degree at most 2AT select such neighbors, one neighbor each. Then all vertices in V of degree bounded by 2AT and their neighbors are removed. We repeat this until no vertices remain in G. Let's look again on the diagram. We can see that first the selection made to V2 and V1, but not to V0, as its degree was not smaller than 4. After the first round, those vertices, V1 and V2, who participated in the previous round are eliminated from our backup placement options. All of their edges are eliminated as well. Now it was possible to create a valid backup placement as U3 chooses V1, V0, and in the last round, we can see how we got it. Now we will show that a considered amount of vertices in V are finished after each iteration. We have managed to prove several interesting traits of the algorithm. First, in each phase, at most half of remaining vertices in V have more than 2AT remaining neighbors each. We lose half of the vertices in each round because if it was not true, we have more than 2AT neighbors to the residual vertices in U, meaning we were left with too many edges, which not represent a true representation of a client-server model. Thus, in the first round of the algorithm, the size of the subset of vertices of V with degree greater than 2AT is at most half of remaining vertices in that phase. Similarly, in the next round, the size of the subset is at most half of the previous subset size, and so forth. After our rounds for a positive integer R, the number of vertices in V with degree greater than 2AT is bounded by n divided by 2 to the power of R. Since the algorithm completes all backup placement in the round when no vertices in V with degree greater than 2AT remain, it terminates within O log n rounds. However, we assume that all vertices know the load value T of the optimum backup placement, but we want to know how they can do so without this knowledge. We use the same principle we used before and iterate over the value of T from T equals 1, while doubling it after each invocation. First time, when T tag becomes at least T, all remaining vertices removed. In this stage, it holds that T tag is smaller than 2T. From here, we can quickly see how the number of rounds required for this computation is O log n log T. However, as O log T executions can be performed in parallel, we get O log n rounds while not knowing T. We also proved that the number of selections of the same vertex in V by vertices in U is bounded by 8AT, a very good result. Let's move on. In this work, we considered sparse graphs such as trees and forests And now we want to generalize to graphs of constant arboricity, and in particular in planar graphs. We will show how in this case, we obtain a constant approximation to Becker placement in O log n rounds. These results suggest that the problem is harder on sparse graphs of high degree than on dense ones. First, what is arboricity? Arboricity is the minimum number of forests that the graph edges can be partitioned into, or the maximum ratio of edges to nodes in any subgraph. For us, the arboricity of a graph is a measure for its sparsity. Sparse graphs have low arboricity. We keep all of the previous assumptions we had regarding the knowledge or obliviousness to T, and vertices still need to know A, although they might intrinsically know it. For example, in planar graphs, vertices know that the arboricity A is bounded by 3. For this, we use the procedure partition algorithm by Barenboim and Elkin. The entire algorithm is quite complicated, so we will focus on our needs from it. You can see its actions on the top diagram. In general, the algorithm receives as input a graph G with arboricity A and partition it to L equals O log n sets, H1 to HL, with time complexity of O log n. Those sets have interesting property. For each vertex in some set, there must be a neighbor in a set with a smaller H index. For example, for a vertex in H2, there must be a neighbor in H1, and for a vertex in H3, there must be a neighbor in H2 or H1, and so forth. For the Becker placement problem, this implies that it is possible to create a Becker placement from any HI, while I greater than 1, to a vertex in Hj, while j is smaller than I. To this end, all vertices in Hi, while I is greater than 1, select in parallel neighbors in sets with smaller indices than their own, one neighbor each. Since the number of neighbors in sets of greater or equal index is bounded by 3a, a property of the algorithm, each vertex is selected by at most 3a neighbors in this stage. It remains to select placements for vertices in H1. For each vertex in H1 that has a neighbor in H1, we select such a neighbor arbitrarily. Since the maximum degree in H1 is bounded by 3a, each vertex can be selected by at most 3a neighbors. However, some vertices in H1 may have no neighbors in this set, but only neighbors in sets of greater indices. So what we can do? We can use our algorithm for Becker placement in bipartite graphs, as you can see in the bottom diagram. We denote as U all of the vertices in H1 that have no neighbors in H1, and as V, all of the neighbors they have in all of the other sets. Finally, the vertices that are neither in U nor in V belongs to H1 and have neighbors in H1. Select arbitrary neighbors in H1 for Becker placement, and that's it. So our results so far are pretty good, but not always the algorithms themselves are pretty and simple. As we want them to be applied for real-world problems, we wonder if it is possible to make them much simpler, step by step, with making them more efficient. Our results focused on any graph with neighborhood independence bounded by a constant C. Although not so complicated, this algorithm still consists of several stages, including a computation of a forest cover, and then handling differently the different parts of the trees, such as leaves and non-leaves. Therefore, we want to significantly simplify the backup placement algorithm for graphs with neighborhood independence bounded by a constant C. So first, let's cut to the chase. We significantly simplified the backup placement algorithm for graphs with bounded independence bounded by a constant C. This is done as the algorithm becomes uniform and consists just of a single instruction that should be executed by all nodes in parallel within a single round. The running time becomes just one round, which improves the number of rounds required in the previous solution for such graphs by a constant. And most importantly, we improve the approximation ratio as well, which becomes C rather than 2C plus 1. Later, we will also show how those improvements can be considered as a natural relaxation of the perfect matching problem. We assume that each vertex knows only about its neighbors, and each vertex has a unique ID. The procedure receives a graph G, VE, as input, and proceeds as follows. We define an operation next modulo that receives a vertex V and a set of its neighbors gamma V in the graph G. We claim that this operation is an optimal backup placement. The operation next modulo selects a vertex in gamma V with a higher ID than the ID of V, and whose ID is the closest to that of V. If no such neighbor is found, then the operation returns the neighbor with the smallest ID. All these selections are performed in parallel within a single round. In the example, we can see a graph in a Rawitz shape with bounded neighborhood independence C equals 4, in which the blue lines exemplified how the backup placement is performed. Let's zoom in to see exactly how each part of the algorithm works and how we prove its correctness. First, next modulo. As we said, each vertex V in V performs this operation in parallel. We have two cases here to demonstrate that action. In the left, V equals 20, and on the right, V equals 95. We can understand now more intuitively that on the left, V chooses 25 as it is bigger than its own ID, but also closer to 20 than 38. On the right, 95 is the highest ID, and thus it chooses the lowest ID among its neighbors, 12. Zoom out a little bit, we will get the following set of selections by next modulo. Now let's prove our claim regarding the load C. Let G be a graph with neighborhood independence of C, meaning for each vertex in the graph with C plus 1 neighbors, at least 2 neighbors are connected by an edge. Then each vertex is selected by at most C neighbors. So assume for contradiction that C plus 1 or more vertices chose the same vertex U as a backup placement. Since the neighborhood independence is C, at least 2 vertices, V1, V2, of the C plus 1 vertices are connected by an edge. Therefore, a triangle U, V1, V2 is formed in the subgraph induced by the edges selected by the algorithm. We will prove our claim by examining each of the 3 possible triangle scenarios. We next show that U could not have been selected by both of its neighbors, V1, V2 in the triangle, when in this example, C equals 4, but for proof by contradiction, we will assume that C plus 1 vertices selected the same vertex U. As C is really 4, then there must be an edge connecting V1 and V2. However, in each of those possibilities, as presented in the example, it is impossible for 2 vertices to choose the same vertex for backup placement. This is because there is always a vertex between V1 and U, or between V2 and U, that one of V1, V2 must select. In any case, we have a contradiction to the assumption that both V1, V2 select U, and we finally proved our claim. Now, as we hold an O1 backup placement algorithm in one round, we can check its applications. We will conclude with a maximum matching approximation. First, let's remind the differences in matchings. A set of edges M in E is called a matching if and only if every vertex V in V belongs to at most one edge in M. A maximal matching is a matching that is maximal with respect to additions of edges, meaning there is no edge E in E, such that M union E is a valid matching. A maximum matching is a matching of maximum size among all matchings of E. And a perfect matching is a matching which matches all vertices of the graph. That is, every vertex of the graph is incident to exactly one edge of the matching. We employ our backup placement algorithm in order to compute maximum matching approximation of an input graph G with neighborhood independence bounded by C. For C equals O1, we obtain a 2 plus epsilon approximation to maximum matching with O log star n rounds. The best previously known O1 approximation for such graph by Barenboim and Maimon has running time of O log delta plus log star n, where delta is the maximum degree of the graph. Another O1 approximate matching result for a narrow family of graphs with bounded growth has running time of O log star n. However, this result of Schneider and Wattenhofer is based on network decompositions, whose computation is in such graphs involves very sophisticated arguments, which we want to avoid. Our algorithm, on the other hand, applies to a wider family of graphs and is very simple. We will explain that shortly. As shown in the previous slides, given a graph GVE with bounded neighborhood independence C, we can compute an O1 backup placement in a single round. This results in a subgraph G tag V E tag, where E tag is the set of all the selected edges of the backup placement algorithm. Each vertex in the subgraph G tag has selected one neighbor and is selected by at most C neighbors, meaning all edges adjacent on a vertex in G tag are either selecting edges or selected edges. Thus, the number of such edges is at most C plus 1. Consequently, the maximum degree delta G tag is at most C plus 1. This is demonstrated in the example on the right, as the red vertex has that maximum degree C plus 1. So how delta G tag can help us in a better maximum matching approximation? We compute a backup placement of an input graph G, obtain the graph G tag VE tag, where E tag is the set of selected edges, and execute a maximum matching algorithm of Patt-Shamir and 𝓒𝓞𝓝 on G tag. The later algorithm computes a maximal matching of an input graph with maximum degree delta within O delta plus log star n rounds. As the maximum degree delta G tag of the subgraph G tag VE tag is at most C plus 1, we get O log star n time complexity of the algorithm. So how this gives us a better approximation? So for each edge in the maximal matching, the orange one in the diagram, we can see that there are at most 2 C+1 vertices, as the vertices includes the vertices of the edge itself and 2 C vertices of the neighbors, since G tag has bounded neighborhood independence C. Therefore, the size of maximal matching of G tag is at least the size of V divided by 2 C plus 1. As the size of maximal matching of G is at most the size of V divided by 2, we get that approximation of C plus 1. In order to reach even better maximum matching approximation than the C plus 1 approximation, we apply several times the maximal matching algorithm by 𝓒𝓞𝓝𝓖𝓔𝓢𝓣 on G tag, which was obtained by the O1 Becker placement in graphs with bounded neighborhood independence C. In order to preserve a proper matching of G, in each step after each computation of a maximal matching, we remove the resulting edges endpoints from G tag, as well as all edges adjacent on these endpoints. Then we invoke again a maximal matching computation on the residual graph. We repeat these actions for a constant number of iterations. As we repeat the procedure, each time C divided by C plus 1 of the vertices are being leaved, and as we returned on this for k times, it converged into an epsilon smaller than 1, meaning that accordingly, we increase mm of G, and so we get an 1 plus epsilon approximation of mm of G. As mm of G is a 2 approximation of MCM of G, we get a 2 plus epsilon approximation. Using O delta plus log star n time maximal matching algorithm by 𝓒𝓞𝓝𝓖𝓔𝓢𝓣, and due to the fact that delta G tag equals C plus 1, which equals O1, each iteration requires O log star n rounds. Since the overall number of iterations is constant, the entire running time is O log star n as well. Now we show an example of this algorithm. It might sound too complicated, but in practice it's simple. The graph with the blue selections on the left is G tag, as we previously showed. Next, we perform the maximal matching algorithm by 𝓒𝓞𝓝𝓖𝓔𝓢𝓣 as it marked in orange. Next, we remove the resulting edges endpoints from G tag, as well as all edges adjacent on these endpoints. We repeat those actions till no vertices left. And as we can see, we finally got a maximum matching approximation. So to conclude this part, given a graph GVE with bounded neighborhood independence C, we achieve a 2 plus epsilon approximation of the maximum matching problem with running time of O log star n, and all of that in a pretty simple manner. To conclude our talk, bounded neighborhood independence is very helpful and should be used as a practical tool in theoretic algorithms. Many real-life networks have constant neighborhood independence, wireless networks, social networks, line graphs, and more, and it really simulate real problems. Such networks admit fast and simple Becker placement solution, O1 Becker placement in 1 round. Talking about the future, so obviously there are many options here as additional graph topologies and even simpler solution for general graph with better approximation ratios. And we hope to see this work helpful in the challenges of the IoT world is facing as soon as possible. That's it. Thank you very much.